Hello students, let's have a quick recap what we have studied in previous lecture, that is solubility of solids in liquids, which depends upon the nature of the solute and the solvent, and like dissolves like, where we have seen that NaCl gets dissolved in water, and for non-polars anthracene and naphthalene gets dissolved in benzene. Now second point is temperature. In temperature we have seen that it follows the Le-Chatelier principle, that is dynamic equilibrium. Equilibrium is dynamic. If the dissolution is endothermic, then heat is absorbed, and temperature, with the increase in temperature, solubility of solute increases, reaction moves forward direction, and for exothermic, heat is released, and with the increase in temperature, solubility of solute decreases, and we have seen that pressure has no impact on the solubility of solids in liquids. So let's move ahead. Now solubility of gases in liquids. Solubility of gases in liquids. Gases dissolved in liquid, we have seen, and we can observe that when we open the cap of a cold drink bottle, you can see the gas sizzles out. Yes, and what does this mean? Solubility of gases in liquids. Gases dissolve in liquids to form homogeneous solutions. And the solubility of gases in liquids depends upon, like earlier we have said that, it depends upon nature of the solute and the solvent. It depends upon the temperature. It depends upon the pressure. So the factors on which it depends, it is nature of gas and the solvent. Then it depends upon the temperature. Then it depends upon the pressure. And then it depends upon the, on the three things, that is nature of solute and solvent. That is, solute can be gas and solvent is any liquid, and then temperature, then pressure. Now let's first talk about nature of gas and solvent. Now you see, nature of gas and solvent. Solubility of gas in liquid is also somewhat affected by nature of gas and the solvent. How? The solubility of different gases is in same solvent varies. If we take the same solvent, same, it varies. For example, you see, oxygen, nitrogen and hydrogen gases dissolves in water up to small extent only. These gases dissolve in water up to small extent only. Whereas ammonia, sulfur dioxide and hydrogen chloride is highly soluble in water. The reason behind is they chemically react with water. So those gases which chemically react with water and forms new compounds, they have high dissolution because they chemically react, and those don't react chemically, they get dissolved in water up to small extent only. Here we see the next factor, the effect of temperature. The solubility of gases in liquid decreases with increase in temperature. Solubility of gases decreases with increase in temperature. You see this diagram. Here you can see at low temperature, temperature is low, and pressure of carbon dioxide gas is high. Temperature is low and pressure of carbon dioxide gas is high in this cylinder. right? But in second cylinder, we can observe that at high temperature, when temperature is raised, here temperature is high now, but the pressure of carbon dioxide gas is low. So it's reciprocal. अगर हम टेम्परेचर को कम करेंगे, तो जो टेम्परेचर अगर लो है, T इज लो, तो गैस जो है वो उसमें ज्यादा है, मोर पार्ट ऑफ द गैस इन लिक्विड. बट इफ वी इंक्रीज द टेम्परेचर को बढ़ा देते हैं, तो गैस जो है वो कम पार्ट होगा उसमें, तो कम गैस जो है वो डिसॉल्व होगी सॉल्यूशन में. So it's reciprocal. So dissolution of a gas in a liquid is an exothermic process. Exothermic process, yes, in exothermic process, heat is released. It follows Le-Chatelier's principle. With the increase in temperature, there is decrease in solubility of gas. This thing you have to remember. In this second graph, we can see that the solubility of NO decreases with the increase in temperature. As the temperature is increasing, the solubility of gas is decreasing. Similarly, for oxygen gas, the solubility is decreasing with the increase in temperature. And similarly, for carbon monoxide gas, the solubility is decreasing, and here methane gas solubility is decreasing, and for N2 nitrogen gas the solubility of gas is increasing. But we can observe from here that oxygen is more soluble, NO is more soluble, and oxygen is less soluble than NO, and whereas N2 is least soluble as compared to the above four gases. So from this we can conclude that with the increase in temperature, solubility of a gas decreases. And let's move to the next. Now, effect of pressure. The solubility of gas in liquid increases with increase in pressure. So when we increase the pressure, the solubility of gas increases. Like the solubility of gas in liquid is highly affected by the pressure. As the pressure of the gas above the surface of liquid increases, it increases solubility of gas. You can see from this cylinder, here the pressure is low. Here in this pressure is low, and we can see very few molecules of gas, or there is no molecule of gas in the liquid. But as we increase the pressure, as the pressure is increased, what do we see? Gas molecules enter in the liquid, whereas in the previous cylinder there was no gas molecule. So from this, what we conclude? We conclude that the solubility of gases in liquid increases with increase in pressure. Moreover, from this graph, you see this is a graph of solubility and pressure. From here, we see that as we increase the pressure is increasing. As we increase the pressure, the solubility is also increased. You see oxygen, the case of oxygen, the solubility is increasing with the increase of pressure, and nitrogen gas solubility is increasing with the increase of pressure, and solubility of helium gas is also increasing with the increase of the pressure. So we see that solubility of gases in liquids increases with increase of the pressure. Now, effect of pressure on solubility. Here we will talk about the Henry's law. Henry's law states that at constant temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. As we have seen here, the partial pressure is directly proportional to the, here we can see solubility of gas is directly proportional to the pressure of the gas. Solubility of gas is directly proportional to the pressure of the gas. So, if m is the mass of the gas and p is the pressure of gas, so we can say solubility, that is mass of the gas, is directly proportional to the pressure of the gas. And we can also write like this: m is equal to k, m is equal to k p, where k is constant of proportionality, and value of k depends upon nature of the gas, solvent, temperature and the pressure. So from here we conclude that at constant temperature, when temperature is constant, the solubility of gas is directly proportional to the pressure of the gas which is present above the surface of the liquid. So we can also write like this: m equal to k into p, where k is proportionality constant and its value depends upon nature of the gas. I mean to say, for different gases value of k differs, and it also depends upon the solvent, the nature of a solvent, and temperature and pressures do affect the value of the k. Now here we will consider the mole fraction of a gas. Mole fraction of a gas. Mole fraction of a gas in a solution to measure its solubility. Then we can say that Henry's law here can be stated that the partial pressure of a gas, that is P, is proportional to the mole fraction of a gas, that is X. X is proportional to P. The partial pressure of a gas is proportional to the mole fraction of the gas. So we can write like this: X equals to K into P, or we can write that P equals to 1 upon K dash X, or we can write here like P equal to K H X. So the value of KH equals to 1 upon K dash. From this equation, what we conclude that the partial pressure of gas is directly proportional to mole fraction, and here X is equal to K dash P, where K is the proportionality constant, and if we write it like this, then rearrange it, we will get 1 upon K dash into X, or P equal to KH X, where KH is Henry's constant. KH is Henry's constant, and it has different values at same temperature. It has, for different gases, it has different values at same temperature. Like we can see here that here nitrogen gas at 293 Kelvin, its value is 74.48, and again nitrogen gas at 298, its value changes, 86 and again at temperature 303 its value is this. Again for oxygen we can see different temperatures, different values. Similarly for hydrogen gas, different temperature, different value, carbon dioxide and methane. So from this we observe that KH value of some gases in water at different temperatures. And now we can conclude from here that mole fraction of gas is directly proportional to the partial pressure, which is Henry's law, and value of KH is for different gases have different KH values at same temperature. That is, KH depends on the nature of the gas. And higher the value of KH at a given pressure, lower the solubility of the gas in the given liquid. So, as the temperature is being increased, the value of KH is increasing. And what does this depict? The increase in value depict that low solubility. As the value of KH is increasing, the solubility is decreasing. Here value of KH is increasing. Value of KH is increasing with the temperature and solubility is decreasing for all the gases. So KH value of particular gas increases with increasing temperature. It indicates that solubility of gas decreases with increase in temperature. So from this table we can conclude that different gases had different KH values at same temperature, and that is KH depends on the nature of the gas, one thing. Second, higher value of KH at given pressure, lower is the solubility. More the value of KH, less the solubility of the gas. And the third point is KH value of particular gas increases with increase in temperature. It indicates the solubility of gases decreases with increasing temperature.